Hello everyone and welcome to Jigyasa Analytics webinar on business applications of AI generated synthetic customer data. My name is Krishna Mehta and my colleague Pat Bhattacharya and I will walk you through the presentation today. Let us start by asking the question, what is synthetic data? It is artificially generated information that mimics real-world data. It is derived using mathematical algorithms, statistical processes, and artificial intelligence. Now, in recent years, the use of data in making business decisions has exploded. We see that in fundraising, we see data being used in marketing applications, customer acquisition, customer retention. We see it in credit risk, in fraud detection, in collections, and many, many more applications. Now, with that have come data security concerns as data breaches are very common. And there has been this push about data privacy for customer data, and there are regulations being put in place for what can the data be used for and how it can be accessed. So, because of all that, it is almost always true for synthetic data applications that it does not contain any direct or inferable private information. Now, synthetic data generation process have been around for some time. There were simulation exercises done earlier where certain distributional assumptions were made, and based on that, uh, certain real world realizations were conjured up, and what the impact would be was calculated. Now, taking that further, in the early 2000s, there was the SMOTE process, which was very promising. But the real advances have been made in the last few years due to the advent of artificial intelligence, particularly in the areas of large language model and computer vision models. And my colleagues will talk more about that, but this has significantly improved the quality and the feasibility of generating synthetic data.
Hello everyone, and thank you for attending this presentation. As Krishna mentioned, recent advances in artificial intelligence and deep learning models have significantly improved our ability to create good quality synthetic samples. For a few years now, deep learning vision models have been used to generate new images. More recently, we have seen examples such as ChatGPT, where deep learning language models are being used to generate new textual content. The success of both the vision and language models have encouraged others in more recent years to use these very same models to generate synthetic tabular data. We decided also to experiment with some of these methods. One of the models that we decided to experiment with creates synthetic tabular data using a large language model. To allow a large language model to work with tabular data, we first have to convert the tabular data to a textual format. For instance, suppose the tabular data contains a value of 50 for the variable age. In order to convert this variable into tabular format, we use the words age is 50. This text is then fed into a large language model, and this can then spit out new synthetic textual data, which again is then converted back into tabular format to get synthetic samples. Another type of model that we experimented with are diffusion models. These models originated in the field of computer vision and are excellent at new image generation. Diffusion models progressively add noise to training data until all features are completely random. The model then learns to reverse the process and create new synthetic samples from noise. Working with these two types of deep learning models, we generated synthetic samples using three approaches. The first approach was based on a large language model and offered us the flexibility of fixing the values of certain fields. For example, we could fix the value of age to be greater than 50 and gender to be female and generate synthetic samples only for that combination of variables. The second approach was also based on a large language model. The advantage of this approach was that it had the capability of handling relational databases. Our third approach was based on diffusion models, which, as I have mentioned, is very popular in the area of image generation. We used two datasets in our experiments. One was a credit risk dataset and the other was a marketing dataset, and we generated synthetic tabular data for both these datasets. One thing I would like to mention here is that all work was done on our own servers with no exposure of any data to the cloud. Once we generated our synthetic samples using deep learning methods, we wanted to evaluate the quality of these synthetic samples. We performed three types of checks to examine the usefulness of these synthetic datasets. In our first experiment, we tried to understand how different are our synthetic records from our real records. Our first thought was that the synthetic records must be very similar to real records in order to be useful. So we tried to see whether a machine learning model can distinguish between our real and synthetic datasets. Our hypothesis is that if these methods cannot distinguish between these datasets, the synthetic data that we generated must be quite similar to the actual dataset. What we found is that while some of the smaller datasets somewhat met this criteria, none of the approaches worked very well on this criteria when we used larger datasets with greater number of features. In the second set of experiments, we tried to evaluate how well the synthetic data preserves the privacy of the original data. Is it possible to get some of the actual data back by reverse engineering the synthetic data? We found that diffusion models performed really well in maintaining the privacy of the actual datasets. Large language models also could preserve the privacy in some cases. We also try to evaluate the utility or usefulness of synthetic datasets. For us data scientists, perhaps the most important measure of utility is how does a model built on the synthetic dataset perform when applied to the actual data. So we went ahead and built machine learning models on each of our synthetic datasets and scored each of these models on a holdout sample of actual data. We found that large language models perform slightly better than diffusion models in our holdout samples, although all three approaches did very well in our holdout samples, generating AUCs greater than 0.74 in each case. So in this final and most important test, all our synthetic samples performed really well. And since many of the samples also preserve the privacy of the true dataset, these deep learning based approaches to create synthetic datasets seem to be very useful and can have many business applications when data is scarce or cannot be accessed due to privacy reasons.
Let me show you the model performance curves for two models. One of these models was built using synthetic data. Pat also in her presentation mentioned how the AUCs were doing very well for all the methods we use for generating synthetic data. But you can ask me the question, that's all very interesting, but we already have actual data. How does that help us? So data append for model development can be an expensive proposition. For a marketing model, you have to do historical append for demographic data, which can add up. And then for financial services, credit risk model, where you have to go to a financial bureau, the bill can be really expensive. And so what if we could substitute out a portion of the real sample, say 25% of the real sample, with uh, synthetic data and lower our costs by that amount. Not only is this a cost savings, but to the extent a model build is less expensive, you can refresh your models more often and have a more up-to-date analytics system. Organizations use models because it allows them to achieve greater efficiency and profits. For example, in the world of marketing analytics, it is not unusual for a customer targeting model to perform twice as better as a random selection. In the world of credit risk, we have often seen a customized scorecard outperform a pure bureau score by 25 to 30%. Now, because of this, organizations and data scientists always want to use a model where available. But I have had so many conversations with clients and colleagues where they want to use the model, but they cannot use it because they lack sufficient data to build that model. What might these cases be? These could be a situation where that organization has gone into a new market, so they do not have any history there. Uh, They have launched a new product, so they have to wait for the sales data to come in before they can get a read. Or it could be a very rare event like fraud, which is rare but is very devastating. So they do want to predict it, but they have to accumulate that critical mass of data before doing any analytics. In all these situations, what if we adopted a bootstrap modeling approach? We start with the limited amount of real data and augment it with a substantially larger amount of synthetic data and build an initial model. Then, as real data starts coming in, the the real component of the sample starts going up and the synthetic amount used in the sample keeps going down, and we have revised models. Using this approach, organizations can start using analytics much sooner in these situations, leading to greater efficiency and profits. Segmenting one's customer base as is an important exercise for any organization. A good segmentation algorithm can improve the performance of a model by 5 to 10%. So, how can synthetic data help with the segmentation process? Let me walk you through an example. We are applying the segmentation algorithm to our customer base, and we get one segment, we get another segment, we get a third segment which is very small, and then we get a fourth segment. So the optimal segmentation leads to a 4 cluster solution. Now, because one of the segments is so small, uh, we would not have the critical amount of data needed to build with that segment. So a very common exercise done in this situation is that we combine the segments and we are left with a 3 segment solution. However, how about we approach the problem a little differently? We take that smaller segment and build synthetic data using the records from that segment and add it to the records already available. And using that, we can reintroduce the fourth segment, and augmenting the smaller cluster with synthetic data will allow us to move towards a more optimal solution. Whenever we use a marketing or a credit risk model to make cutoffs based on scores, there is going to be a section of the universe that was code which is rarely selected. This section obviously has very low affinity based on the predictors used in the model. Now, as this continues over time, this group is very underrepresented in the original sample. And so for future model builds, the marketing or the uh, or the credit risk sample will have an underrepresentation of this section of the people. And because the model is designed to score everyone, not just the people you approve or who actually respond to the marketing or get selected by the marketing, there is going to be a bias in the model, and which will lead to lower performance. Now, this issue is known. In marketing, we try to address it using different sampling approaches. In credit risk, we often do reject inferencing using bureau data, or we use additional statistical methods as well. Now, what if we instead also tried synthetic data? So we could use the underrepresented group, we could add synthetic data similar to this group, use this group to create the synthetic data, and then augment the sample with this synthetic data, leading to a model with lower bias. It is exciting to be in the data science field right now with all the advances we are seeing in artificial intelligence and data science, which make a lot of analytics possible, which was not possible earlier. However, the adoption lags by years often because of the challenges an organization faces. These challenges might be, some of them might be technology related, making everything sync up, but more often than not, a big component is the risk of exposing customer data to unknown external technology. A lot of times these are available initially in the on the cloud, so it means taking the customer data out to the cloud to test out the technology, or if you are bringing the technology in house, whether it will open security gaps within your system. All of this takes time to figure out. And this gives us another area where there is opportunity to use synthetic data, because uh, the new technology could be tested out with synthetic data, reducing the risk to actual data. And once it has been validated and is known to be secure, then it can be brought in for use with real data. Usage of consumer data is heavily regulated by privacy laws that restrict how data can be gathered and used by an organization. Examples are GDPR in Europe, CCPA in California. Other states are also coming up with that, and then other industries apart from marketing have their set of regulations as well. Apart from usage restrictions, these regulations also have strict consent and opt-out requirements. What all this means is that this has led to a severe limitation in way consumer data can be used and how models can be built using that consumer data. Now, synthetic data provides organizations with an alternate source of data, and while it might not solve every issue related to consumer data usage, it can certainly help in certain areas, and it is worth looking into. So what is next for us in our AI research? For synthetic data, we now want to customize our findings for specific industry solutions. But we are doing a lot of research on other AI areas as well. In particular, we are working with computer vision models to combine image and textual data and use them in predictive models. And we are very excited with the results we are seeing in this area. And we look forward to bringing a webinar on this to you sometime soon. In all of this, we love to have you on board as a partner. So if your organization is interested in joining these experiments, please let us know. I would like to thank you so much for joining us today and listening to our presentation. I would also like to acknowledge my colleagues Shikha Agarwal, Ratna Sinha, and Barkha Agarwal, who made significant contributions to this project. Now over to question and answers.